Hello everyone, in this video we are going to be looking at the three laws of motion. So first, before we start talking about the laws of motion, let's just remind ourselves about two concepts. First, object has inertia. So unless we have an unbalanced force that is applied to the object, it is going to keep where it is at and resist the change in motion. So it's going to stay at rest or continue on its constant velocity, but unless we have an unbalanced force applied to it. The second is forces are involved when we are looking at the change of motion. Starting with Newton's first law of motion, it states that every object remains at rest or in its state of uniform straight line motion unless acted upon by an unbalanced force. Looking at this, well, we can see that it is essentially describing what we just said, the tendency of an object to resist any changes in its state of motion. And since this is the definition of inertia, it is also referred as the law of inertia. So a couple of things that we experience then Newton's first law is, well, when the bus is at rest, when you're sitting on the bus and then the bus was at rest at first, but then it starts to move forward. The inertia is going to cause us to remain in the original position and appearing to fall backward. So it's just like when you're starting the car at the beginning, you're going to feel like, okay, something is keeping me pushed towards my back seat. Well, that is inertia. And another thing that we can experience is, well, when the bus turns. So if you're on the bus, when the bus turns, you can feel that, well, let's say the bus is turning right. You can feel that you are going to be pushed towards the left because you want to remain in the same position. So this is also inertia because the inertia is causing the person to retain the original straight line motion until it's forced into a new direction by the side of the bus. So the person wants to keep going forward, but the bus already turned. So you are going to feel like, okay, when you're driving or when someone else is driving, you can feel the turn, and that's also can be explained by the first law of motion, or in other terms, that is an evidence of the Newton's first law of motion. The second law of motion is, well, we observe two things, right? The net force is zero when we are moving at a constant speed in a straight line. We discussed this previously. If you are wondering what I'm talking about, remember to refer back to our previous discussion. And the acceleration would only occur during the time when the net force is greater than zero. So when we are decelerating, that means that our net force is less than zero. So this unbalanced force is the one that produces acceleration. Looking at this, well, Newton concluded this observation and say that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the mass of an object. So with that said, well, we can basically conclude that, first of all, based on the sentence, acceleration is directly proportional to the net force, and it is inversely proportional to the mass of an object. So concluding this, we can change this into an equation that is F equals to m times A, where F is the net force, so it's the force, m is the mass in kilograms. So note that right now we are starting to include the units because we have to make sure the units are in these before we can plug it in. So we have to convert the units into the listed indicated unit before we can plug it into the equation. And A is the acceleration, and that is in units of meters per second square. So now let's take a moment to look at what would the unit of force be. So for the force, well, it's m times A. So the unit of force is going to be m, which is kilograms, multiplied by A, which is meters over second square. So the force's unit is going to be kilogram times m over s squared. And this is a definition of a Newton. So the unit of force is Newton. So 1 Newton is equal to 1 kilogram meter over s squared. And that is a new unit that is specific to the force that we are describing. And this equation, it defines a concept. So over here, it defines a concept. It defines what it means by a force. Therefore, we considered it as a operational definition. So operational definition, because this tells us how force are defined and how it can be measured. And remember, when we are using this equation, we have to change the variables into these corresponding units before we can use the equation. So with that idea in mind, let's look at this problem together. So a 60 kilogram bicycle and rider accelerates at 0.5 meter per second square. How much extra force was applied? Looking at this, well, first, let's again start by listing down the things we know. So we have a 60 kilogram bike and the bike rider. So the mass is 60 kilogram. And then it is accelerating at 0.5 meters per second. So the acceleration is 0.5 meters per second. It is asking us how much extra force. So we know that we are looking for force. So with these, we know that the equation we are looking at is F equals to m times A. So the equation is already solved because F is already by itself on one end. And that's the second thing let's look at is the units, right? We need the terms to be in appropriate units. So mass is in kilograms, acceleration is in mass per second square, so all the units are in place, so we don't need to convert the units as well. So what is left is for us to plug the numbers in. So F is equal to m, 60 kilograms, multiplied by A, 0.5 meter over second square. So again, we will be combining the numerical part. So 60 times 0.5. And then combining the unit part, kilograms times the meter per second square. So we get that this is 30 meters per second square. So kilogram meter per second square. Okay. It's kilogram times meter per second square. And remember, this by definition is a Newton, so we can also say it is 30 Newton. And for this example, I hope that you can take some time to pause the video, try it yourself, and then come back when you are ready. Welcome back. So looking at this example, again, we are going to start by reading the question and making a list of things we know and things that we are trying to find. So first it says, what is the acceleration of a 20 kilogram cart if the net force on it is 40 Newton? Looking at this, well, we know that we have a 20 kilogram cart, that is our mass, is 20 kilograms. And then the force exerted on it is 40 Newton. So the force is 40 Newton. We're looking for the acceleration. So A is what we're looking for. In this case, we're again going to use Newton's second law, F equals to m times A. And because we are looking for A, we're going to try to rearrange the equation so that way A is by itself. We can do this by dividing m on both sides. That way the m over here will cancel out and we'll have F over m equals to A. The next one is we have to check the units. So based on the equation, F needs to be in Newton, which it is. M needs to be in kilograms, which it is. So we are done. We don't need to convert any units in addition to what we already have. And then lastly, we solve for it. So we know A equals to F over M. So that is 40 newtons over M is 20 kilograms. So let's look at N divided by kilogram. So remember, 1 Newton is equal to 1 kilogram times meter over S squared. So we can express that as kilogram times meter over S squared divided by kilogram. So that is the unit for N over kilograms. So looking at this, well, again, we are going to do the math for 40 divided by 20. And then the unit is N divided by kilograms. So that is 2. And looking at the kilograms meter over second squared divided by kilogram, we know that we can simplify this into kilogram times meter over second squared multiplied by 1 over kilogram. And the kilogram cancel out. We are going to get meter over second squared, which is the correct unit because we're looking at acceleration. And acceleration is in the units of distance over time squared. So the answer will be 2 meter over second squared, and that will be our acceleration in this particular case. So, well, now that we have discussed mass being involved with force, let's take a closer look at what mass is. Because previously we discussed how mass and weight are different ideas. So now let's look into it with the things that we know now. So first we know that mass is a property that determines how much an object resists the change in its motion. So essentially, mass is super similar, or it's closely related to inertia. The greater the mass, the greater the inertia. On the other hand, the weight is a measure of the force of gravity acting on an object. So fundamentally, they're different. And if we look at it, well, we know that F equals to ma, that's our Newton's second law. This m over here is the mass. However, how can we describe this in terms of weight, right? Because weight is the measure of a force of gravity acting on an object. So by definition, weight is mass, multiplied by gravity. And that is acceleration due to gravity. Remember, that is our little g. So W is our weight, M is our mass, and G is acceleration due to gravity. And that is 9.8 meter over second square if we are on Earth. So that means that, well, mass and weight are actually going to have a different number that we're looking at, right? Because, well, based on what we just defined, mass is going to be in kilograms, and the force is m times a, right? And this is the force. So when we're looking at an English system, it turns out that pounds is actually describing a unit of force. So that is just something that I figured it is interesting. And when we are looking at the net force, well, we can think about it as when we are holding a ball in our hand. Well, when we are supporting the weight of the ball, we hold it stationary essentially. So the upward force of our hand and the downward force of the ball, which is its weight, is equal to a net force of 0. And when we let go of the ball, so just drop the ball on the ground, the gravitational force is the only force that is acting on the ball because it's dropping, right? Originally, we were holding it in our hand, and now the ball is dropping. So we have the gravitational force acting on the ball. And this ball's weight is then the net force that accelerates it at the acceleration of gravity, g. So we can say that the F net at this point is equal to weight, which is equal to mass times acceleration, which is mass times acceleration of gravity. So the weight of the ball never really changes in a given location. So the weight is always equal to mass times gravity, even if the ball is not really accelerating, because gravity is going to always be there for us. So basically that is the differences between mass and weight, because weight is mass times gravity. So the gravity is always in there acting on us. So the ball, regardless of whether the ball is accelerating or not, is still going to experience this gravity. So the weight of the ball is not going to change. And that is just something that we need to keep in mind when we're looking at weight and mass. So looking at an example over here, so it is asking us what is the weight of a 60-kilogram person on the surface of Earth. So first of all, we know that we are looking for weight, right? Because it says, what is the weight? And then the second thing we know is that the mass is 60.0 kilograms, because it says 60.0 kilograms. And then we are on the surface of Earth, meaning that the gravity, or the acceleration of gravity, little g, is going to equal to 9.8 meter over second square. So then to do this, well, we know that weight equals to mass times g, the acceleration due to gravity. So we are solving for weight, which is already by itself, so we can go ahead and do the math part. And with this, well, what we can get is that weight is equal to mass, which is going to be 60.0 kilograms multiplied by 9.8 meter over second square. And again, we are going to do the number part by itself and then do the unit part by itself. So the number is 60 and 9.8, and we're multiplying. So 60 times 9.8 is 588. And then we'll look at the units. So kilograms times meter per second square, that is kilograms times meter per second square. And this unit is equal to a Newton. So every time you see this big chunk, you know this is Newton. So then the weight of this person on the surface of Earth is 590 Newton. So note that we can see that weight over here, it's actually showing the same unit as force. So next time when we are looking at weight and mass, just remember they are different things by definition. So for this question, I hope that you can take some time, pause the video, try it yourself, and then come back when you are ready. So welcome back. In this question, it says that a 50.0 kilogram person weighs 100 Newton on the moon. What is the acceleration, gravity on the moon? So in this case, first of all, let's again start by listing down the things we know. So first we know that this person is 50 kilograms. So the mass of this person is 50 kilograms. And then the weight is 100 Newton. So we know that the weight is 100.0 Newton. It's asking us the acceleration of gravity on the moon. So we were just going to say it's g for the moon in case we got ourselves mixed up. And what is this? So again, we're going to start by using the equation W equals to mass times gravity. So if it is on Earth, it's 9.8. But now we're on moon. So we're going to be using a different g in this case. But before we even do that, well, let's look at how we can rearrange this, right? We are trying to find g, so we have to get g by itself. We can do that by dividing both sides by meters. sorry, not meters, mass. So we can get gravity is equal to weight divided by mass. And remember, this is the gravity of the moon. We're not on Earth anymore. So the gravity of the moon is equal to weight, which is 100.0 Newton divided by 50.0 kilograms. And then with that, well, again, we are going to do the math with the number by itself. So that is going to be 100.0 divided by 50. That is our number part. And then our unit is Newton divided by kilograms. And for newtons divided by kilograms, remember, Newton is kilogram times meter over second square. This divided by kilograms is basically the same as kilogram times meter over second multiplied by 1 over kilogram. We can see that our kilograms is going to cancel out, so it's going to be meter per second square. So at the end of the day, well, this person is going to be 2 meter per second square. And that is not this person, sorry. The acceleration of gravity on moon is 2 meter per second square. So we can see that over here, well, the G on Earth and on moon is vastly different. And this is why when we are looking at gravity, when we're looking at mass and weight, we stress that the mass is the same regardless of whether you are on Earth, on the moon, on Mars. Your mass is not going to change. But your weight is going to be changing because your weight depends on the gravitational pull of wherever you're at. So on Earth it's 9.8. On moon it's actually around 1.67. So that is just something that we need to make sure we are making clear distinguish. So coming back, let's look at Newton's third law of motion. So in Newton's third law of motion, it's describing what happened between two objects. So it's key that in the third law of motion, we're looking at two different objects. We're going to say that, well, a single force does not exist by itself. There's always an equally sized force, but opposite in direction, that occurs at the same time. And these forces are at every instant is caused by each other. So when they appear, the two forces are going to appear and disappear at the same time. We can imagine that we have an astronaut pushing a satellite or a spaceship. When the astronaut pushes a spaceship, the astronaut is going to experience a force by the spacecraft pushing this way. And then the spacecraft is going to experience a force that is exerted by the astronaut pushing this way. So the astronaut pushes the spacecraft, there's going to be a force going from left to right. But at the same time, there's an equal size of force that is exerted on the astronaut by the spacecraft, going from right to left. And this is why when you push things, when they actually push, they're actually going to be moving this direction, right? They're going to be pushed away from each other. So putting it in terms, it says that whenever two objects interact, the force exerted on one object is equal in size and opposite in direction to the force exerted on the other object. And this can be described by the following. So the force that is on A due to B is equal to the force that is on B due to A. And then we can look at this in more detail. So first of all, A due to B is the force of that we experience due to someone else pushing us. B due to A is the force that someone else experienced due to us pushing it. And remember, based on the second law, F equals to ma, right? We know this. So we can also further written this as, well, this F can be broken down into m times A, right? So this, we can rewrite it as mass of A times acceleration of A. And this is going to equal to, well, this is the force that B experienced. So this is mass of B multiplied by acceleration of B. So basically, we are combining the second law and third law together. The force that is exerted on, let's see, we have an A and a B. So when A exerts a force on B, this force is going to equal to the mass of A multiplied by the acceleration of A. And then this force is equal but opposite to the force that B experienced because of A. And this is going to equal to the mass of B multiplied by the acceleration of B. Looking at the example problem here, it says that we have a 60-kilogram astronaut is freely floating in space and pushes on a freely floating 120-kilogram spacecraft with a force of 30 Newton for 1.5 seconds. The first thing we are going to do is to compare the force exerted on the astronaut and on the spacecraft. So, the astronaut is pushing on the spacecraft. We're just going to say this is a spacecraft. I don't know why I draw it that way. And that is 30.0 newtons. So remember the Newton's third law. That means that the spacecraft is also exerted a 30 Newton force on the astronaut. So they are going to be the same. And then they are both going to be 30 newtons. So we are going to write same 30.0 Newton force is exerted on the astronaut, which is by the spacecraft, and on the spacecraft by the astronaut. Okay, I'm running out of space. Astronaut. Cool. Yeah, I trust that you can figure out the spelling up here. So, for part B of this question, it is saying that, well, looking at the same condition, we're going to compare the acceleration of the astronaut to the acceleration of the space. So then that means that we are going to do two calculations, one for astronaut and one for the spacecraft. So first, let's look at the one for astronaut. So for astronaut, we know that, well, this astronaut is 60 kilograms. So we know that its mass is 60.0 kilograms. And then we know that the force it is pushing is 30.0 Newton because it pushes with a force. We're looking for acceleration. From here, we know that we can look at F equals to M times A. And then with that, we are going to try to get A by itself, so we'll divide both sides by M. So then we get A equals to force divided by mass. Then we can calculate. So it's the acceleration of the astronaut. That is going to equal to force 30.0 Newton divided by mass 60.0 kilograms. And this is 0.500 meters over second square. And the conversion for how newtons divided by kilograms is equal to meter per second square, we discussed that previously, so I'm not going to go over it over here. And we're going to do a separate calculation for the spacecraft. So for the spacecraft, we again are going to collect a set of data. For this spacecraft, it is 120 kilograms. So its mass is 120 kilograms. Oops. Okay. I'm going to erase these so that way I have space. So the spacecraft, so the mass for the spacecraft is 120 kilograms. And then the force is the same 30 newtons, right? We discussed that previously, that they're the same. So we're going to, again, try to calculate the acceleration. So we already figured out the equation solving because that's the same as the astronaut. So the acceleration of the spacecraft is going to equal to, well, 30 Newton, it's force, divided by 120.0 kilograms. It is equal to 0.25 meters over second square. And again, we do the numbers part by itself and then the unit part by itself. And these are our two answers. So even if we have the same force, we are actually we end up accelerating at different speed because we have different mass. So that's why sometimes when you are pushing let's say you're pushing a skateboard along the ground, the skateboard is going to just, when you push it, it's going to just keep going far end of the other street, but you are going to stay the same. It's because your mass and the mass of the skateboard is so different that the skateboard is having a gigantic acceleration, while for you, while there are a lot of other forces involved, for you the acceleration is going to be much smaller because the mass of a person is greater than the mass of a skateboard. So over here, we are going to look at another example. I hope that over here you can take a moment to try it yourself and then see how far we can get, and then we can come back and look at this together. Welcome back. So for this problem, it says that, well, we still have the 60-kilogram astronaut that is freely floating in space and pushes on the freely floating 120-kilogram spacecraft with a force of 30.0 Newton for 1.50 seconds. After both of them move away from their original position, what is the new speed for each? So we're looking for speed this time. So again, since they are looking for speed, we are again going to have a case for astronaut and for the spacecraft. So astronaut. And then for the astronaut, previously we found that the acceleration for the astronaut is 0.500 meters per second square. We know that initially both of them has a velocity of 0 when they push it, right? We stay still and then we push. So the velocity initially was 0 meters per second. The time that it pushed is 1.50 seconds. And we're looking for the final velocity. So in this case, well, the equation we'll be using is the equation for the acceleration, right? Acceleration is equal to Vf minus Vi, final minus initial velocity, over time. And we can rearrange this because we're looking for Vf, so we want to get Vf by itself. So we start by multiplying t on both sides. So then we'll have A times t is equal to Vf minus Vi. Then we will add Vi on both sides. So then at the end of the day, we get A times t plus Vi is equal to Vf. And this will be the equation that we will be using to solve the math. So Vf for the astronaut, let me write it. So Vf for the astronaut is going to equal to A times t. So A is 0.500 meters per second square, multiplied by t, 1.50 seconds, plus Vi, which is 0 meters per second, and this is going to equal to 0.750. And again, let's look at the math part. So we're going to get the numbers. So these two numbers multiply by each other. Since we're adding zeros, I'm just going to disregard this. And then our units is going to be meters over second square multiplied by seconds. So one of the seconds will cancel out, giving us meters over second. And this is the velocity of the astronaut after they pushed away from each other. Now let's look at the velocity for the spacecraft. So for the spacecraft over here, previously we found that the spacecraft is going to have an acceleration of 0.250 meters per second square. The velocity at the initial contact is still 0. The time that is being pushed is 1.5. So we're looking for final velocity. So in this case, well, again, we already solved the equation because we're using the same one. We're still looking for the final velocity. This is equal to, again, A, which is 0.250 meters per second square, multiplied by the time of contact, 1.50 seconds, plus the initial velocity, 0 meters over seconds. So this is 0. I'm again going to disregard that. And we are going to once again multiply by the number. So 0.25 times 1.50, that is 0.375. Looking at the units is meter over second square multiplied by seconds, and that is going to be meters over second. So meters over second square is the same as meter over second times second. So meters over second times second multiplied by seconds is going to be meters over second. So that's why that will be our answers for the question. With that idea in mind, thank you for watching this video, and I'll see you in another one.